Yeah, thank you, Kaya. Yeah, hello everyone. I'm not sure how to say hello because the time differences are quite wide here. So yeah, as introduced by Kaya, my name is Wook Jo from Ulsan National Institute of Science and Technology. Today, I'm planning to talk about some state of the arts and the development of lead-free piezoceramics and something uh, I I am my colleagues have been doing in units at the current position. So this is the title, and the main the guy who did this the most of the works I'm gonna present at the end of this talk was given by Hwang Pil Kim, who's my PhD student, and yeah, this is my name Wook Jo. So yeah, before we start, it's I think it's a good idea to think about some of the questions like everyone try to develop wonderful and excellent functionalities in piezoelectric ceramics, but they often forget to ask these very essential questions like how good is good enough? Everyone says they made a good piezoelectric ceramics, but no one really knows which one how good is really good. So this kind of question should be addressed before we actually discuss the state of the art and the uh, upcoming research topics. And second would be most of the papers are reporting that they applied MPB, morphotrope phase boundary concept to develop new composition, new lead-free compositions, but it seems that the MPB concept, MPB strategy it's not really the working in the lead-free piezoceramics, even though there are some of the extraordinary achievements, but MPB doesn't seem to be quite working just like in PCT ceramics. And the third question would be like, yeah, where right now, what's the state of the art and the development of lead-free, and where do we have to go further? This kind of question should be addressed to better, uh, better uh, to be more efficient in developing new type of piezoceramics. Now, since most of the people already know the regulation things, environmental regulation things on the piezoceramics. So I don't really have to talk about that. But thing is that even even today, we never hear the entire ban on the use of lead in the piezoceramics. That means the lead-free piezoceramics is a kind of proper future direction of our development, but we should not really confine to the lead-free stuff, removing all the toxic stuff. The the reason is I often think about why lead-free has inferior properties than lead-containing counterparts. The answer seems to be quite straightforward and simple because our body is a food of water, which is a polar material, and all the nice piezoelectric materials based on the ferroelectric materials, based on the ferroelectricity, also requires a high polarizability. That means polar material go together with the polar. That means, if you want to develop something wonderful in terms of polarizability, which is not harmful to human health, doesn't seem to be working together. So that's why the lead-free is a very important topic and a very important subject to be further studied, but we cannot really fully devoting to the elimination of lead at the end. This is just my personal opinion, and some of you might not agree with me, but this is how I feel. So that's why at the end of this talk, I try to propose some of the other techniques to get the better piezoelectric, lead-free piezoelectric ceramics using different approaches other than MPB. So if you look through the literature, you can see a lot of what record-breaking achievements. Like, for example, here most of the things, if you look at these papers, and most of the papers are claiming that they have wonderful material developed. Like D33-wise, this achieves certain value which has never been achieved before, something like that. And that people also know that they already know that if they want to have a better piezoelectric coefficient, they need to sacrifice the Curie temperature. But in the real-time applications, these days I'm devoting myself largely to the real-time applications. And what I realize is that Curie temperature is really important, even though people usually sacrifice Curie temperature to get better piezoelectric coefficient. The reason is quite simple. If you want the piezoelectric element cannot stand alone for device applications. There has to be attached to somewhere. For that, you usually use epoxy, the glue. The glue usually, the glass transition for the glue, the typically available glue has a glass temperature at around more than 100 degrees C. That means Curie temperature, if the Curie temperature is less than 100 degrees C, the material cannot be used for that applications. So there are many other reasons why we have to also consider Curie temperature. We're gonna talk about that a bit later again. So like I said, everyone says they, broke the record and they're getting the usable and potentially important lead-free piezoceramics. But the problem is that still we never seen the introduction of lead-free piezoceramics to the industry. Why is that? Because the piezo coefficient itself, piezo coefficient is really important, but that doesn't make everything everything okay. That's one of the reasons. Again, another state of the art I can introduce you, it would be like recently in the case of potassium sodium niobate based lead-free piezoceramics, people started working another type of MPB, multiple phase bonding, which is rhombohedral heater versus tetragonal. The kind of DMPB we are quite used to from the PZT based materials. Here, one of the noteworthy achievements is given by Jia Gang in Sichuan University. It seems that these days he's the only one who's breaking the record again and again. And then at the moment, officially, unofficially, the piezoelectric coefficient he reached it, or he achieved was somewhere around 600 picocoulomb per Newton, which is really, really high value. The background, the mechanism behind that is not fully understood, unfortunately. So, but nevertheless, MPB, this new type of MPB seems to be working. And alongside, there are several other research groups who are also working on different techniques instead of MPB. Probably the base composition comes from the MPB composition, but they apply different techniques. For example, grain-oriented lead-free piezoceramics through the templated grain growth. The idea is really simple, and when it comes to piezoelectric materials, single crystal should have the best properties because all these spontaneous polarization aligns along the same crystallographic direction, which gives the best performance of the piezoelectric materials. So grain orientation, even though the achieved value here is not that high, one interesting thing is if you apply this templated grain growth technique, even though the D33 is not that high, but strain seems to be enhanced quite a lot. I'll talk about that later, the interrelationship between strain and the piezoelectric coefficient, but grain-oriented, the templated grain growth seems to be very useful if you consider high strain material, and we're going to talk about that later. In the meantime, we have another good achievement using completely different technique, which is called water quenching. Because when it comes to bismuth ferrite, you know that the spontaneous polarization of bismuth ferrite is so high that it could be a really nice ferroelectric material, but the problem is you cannot get a phase pure bulk bismuth ferrite materials because of the metastable phases in between cubic point and room temperature. So what these people did was to quench the sample from the temperature where this metastable phase doesn't exist, quickly bring it down to room temperature so that they can get a phase pure lead-free materials, the phase pure bulk materials. But as you can imagine, the problem would be like thermal shock. I've never seen the samples they produced, but we try to repeat the experiment in our laboratory. We found that, yeah, at least from the scanning electron microscopy, with a lot of microcracks existing there. Yeah, of course, since a electromechanical material, piezoelectric is an electromechanical material, which means that it vibrates all the time. That means the microcracking should be a kind of big problem there. So this is a kind of a brief review on the state of the art. And before we think about new strategies to develop some desirable material, it seems that it would be nice if we think about some of the fundamentals here. So I just bring your attention to this fundamental aspect here. As you already know, the reason why people are crazy about MPB strategy is just because, yeah, when there is a phase transformation, bulk modulus goes down. That means material becomes softened. That means the electromechanical property tends to be enhanced. This is one of the reasons. Phase coexistence is always kind of a key to enhance piezoelectric properties. That's why, as you see here, we see that whenever we go across certain phase boundary, we have we have an enhancement in the piezoelectric properties. This is a case for the barium titanate on the left-hand side, but on the right-hand side is the potassium sodium niobate, potassium sodium niobate ceramic. Even here, you see that when the phase transformation is happening from orthorhombic, low temperature orthorhombic to high temperature tetragonal, we see a slight enhancement in the piezoelectric properties. But something we have to keep in mind is that, yeah, phase boundary is really good for enhancing piezoelectric properties. But in the meantime, it's really harmful for practical applications because whenever you go across this boundary, you start to lose piezoelectric properties because the phase transformation changes stable spontaneous polarization direction. That means once crystal structure is changing, some of the part of the spontaneous polarization depots. That's why you start to lose the piezoelectric properties. Degradation happens. So many people, whenever people try to develop new piezoelectric composition, they always talk about high TC. So they try to get a base material with a high TC because high TC means thermal stability is better. But here, what I want to say is that TC is important, but if you have a material which undergoes a series of phase transformation, at least a single phase transformation, and TC doesn't seem to be really meaningful. So the question throwing here is, when you develop new material, do you have to consider TC or TD? I would say TD is more important, depolarization temperature. It could be phase boundary, the polymorphism, during the polymorphism phase boundary could be TD. When it comes to single crystal, people usually say TRT, rhombohedral to tetragonal phase boundary, or it could be freezing temperature if you deal with the relaxed materials. So the reason TD, TC is important can be really straightforward from this example here. probably you saw this type of plot a lot in the literature, because this is really a famous one. But whenever I see this kind of plot, I usually remove this eye guide here. So eye guide is sometimes really misleading me. So if just imagine that there is no eye guide here, that means that you only have a dots here, square dots. And then do you see that this trend is really like this curved one? To me, I also see dots down here too. That means to me, it looks like just a linear line. So I just assume that, what if this is really linear line? And then I plot everything again in terms of linear line, but not just the Curie temperature, but reduced temperature. I call reduced temperature. That means since the D33 value should be measured at room temperature, so the points represent D33 at room temperature. That means we cannot really compare the room temperature D33 as a function of Curie temperature, but maybe reduced temperature. In this case, room temperature normalized by Curie point. Because at least in this PCT materials, we don't have a phase boundary in between TC and room temperature. So I just plot them, and this line is not eye guide. This is a fitting line. If you look at this fitting line, it fits very nicely with the linear line. Then why did I do this? Because this gives us a really good insight how to enhance the piezoelectric properties of certain new compositions. So I also put the relaxed PT-based materials too. They also fit very nicely into this line. So this line means you don't really have to think about practical window here. But this line means you see that this is exactly the data I showed you in the previous slide for the PCT together with the relaxed PT type of ceramics, the D33 as a function of this reduced temperature. And this line really goes like linear. And then that means if you bring down the Curie point or depolarization temperature very near to room temperature, the maximum D33 from D33 expected from this polycrystalline ceramics would be somewhere around 1100 picocoulomb per Newton. So that means you cannot really go above this 1100 picocoulomb per Newton. Maybe, but this is just a kind of empirical, as the prediction. That's why some might go even above this value with a little bit higher Curie point, but at least this is this gives us a kind of direction, how where we are heading towards, like. So 1100. So, but we have a huge empty space up there. How do you achieve this? How do we get certain material with this high value of piezo coefficient? And I just did another research, another survey on the literature, and one of the ways to overcome this the limitation would be to work with a single crystal. Single crystal, even though it doesn't fit in any, the linear line for any tendency, but anyway, most of the single crystal, relaxer-based single crystal goes above this upper limit. And this is not all, we have another, we can also do another, the analysis on even on the lead-free piezoceramics we are interested in. So you remember this is PZT line, goes up to about 1100 degrees. So I collected some of the accepted data on lead-free piezoceramics, and I plot them in this reduced temperature scheme here, not the TC, but the reduced temperature. In this case, reduced temperature means TRT or TOT in the KNN-based materials. When it comes to bismuth sodium titanate-based materials, it could be TD, depolarization temperature, where relaxer goes into ferroelectric. So I just plot them randomly here. And I also noted that this also goes fits into a single line very nicely into a single linear line. And the limit of the maximum D33 we can achieve once we bring down this depolarization temperature to room temperature will be somewhere around 400. So this already explains why PZT is so amazing material in comparison to lead-free materials. So we cannot really go over this line. So again, how do you overcome this limitation? Yeah, first possibility would be to make single crystal. So if you work with a single crystal, it can even reach the value near PZT. Of course, this is again, this is from the data I collected from the available literature. So this cannot really represent all the materials we have in the world, but at least, like I said, at least this gives you a kind of insight and the kind of the goal we can achieve. Yeah, it's just helpful in better understanding how to develop, how we can expect, what we can expect from our the research activities. And the single crystal, of course, gives you really wonderful properties, as you can see here, but single crystal is not really cost effective. It's really expensive. That's the first. And then single crystal is highly fragile. That's another problem for real-time applications. So I also did another survey on the literature and then found that, yeah, texture is another way to make properties to overcome these limitations. And this is from the texture BT-based materials. You see that at least this is far away from, far away from the, what happened? Far away from the limitation here. And if you look at this is a well-known composition from the Nature paper, Saito et al. And as you can see here, the reason this material became really famous is because this fits in very near to PZT line here. Of course, inside this, the processing window. So this is really workable. And another interesting stuff is that the water quenched bismuth ferrite-based material also fits into PZT line here. So that means all three techniques, single crystal or LF4T is also textured material, and water quenching, they all seem to give some unexpectedly nice results, better than you expected. So this literature survey summarizes into the three techniques to be of potential interest. As I already told you, grain orientation, we say TGG, temporary grain growth, and water quenching, and single crystal. These three will be, I think, should be highly utilized for the people working in the lead-free piezoceramics afterwards. But the one comment is the water quenching. This is actually taken from my lab. This is my first PhD student. You see, this is really scratchy. It's not really safe. So once he first did that, and I said, please don't do that. That doesn't look really good, and it doesn't have, it doesn't seem to have industrial impact neither. That's why water quenching, I just asked for possibility in future research. And single crystal, as I already told you, is too expensive, as well as the composition is not really reliable because it changes it changes a lot from the fabrication method to fabrication method. So in our lab, we are focusing highly on the grain orientation technique here, TGG. So after this slide, what I want to show you is one of the examples how we utilize this technique to have a new type of lead-free piezoceramics. Okay, so for your better understanding, maybe some of you might ask like, yeah, we know that there are a lot of wonderful electric piezoceramics already introduced in the literature. Why they cannot be applied to the industry? The reason is simple. This is some examples of applications at which requires the cutting edge state of the art the piezoceramics. All these the high-end high-end applications requires high SMAX Emax. So D33 is not the equal to SMAX Emax because when it comes to normal piezoelectrics, it's identical because it only gives you linear correlation between electric field and strain behavior. But when it comes to ferroelectric based piezoceramics, the problem is we have ferroelectric domains in there. That gives you hysteresis. That's why domain contribution usually deviates D33 from SMAX Emax. The example is like this. This is from the commercial PCT. This is bipolar strain behavior. And as you already know, I usually call this a red line as an engineering strain because a real-time application only requires a unipolar strain. That's why engineering strain. But if you want to understand the underlying mechanism, you probably need to have this bipolar strain. That's why this is scientist's strain. But what I want to point out here is that this is the maximum strain. The difference between maximum and this remnant strain is called unipolar strain. But if you look at this line here is called SMAX Emax. This is a SMAX Emax, but D33 is just a slope. This slope is just simply D33. Even in the PCT, the SMAX Emax is a lot bigger than D33. Sometimes unipolar strain goes like this. In this case, D33, even the D33 is really high, SMAX Emax could be really small. So the focus should not be, if you consider the application, practical application, focus should not be on D33, but SMAX Emax. So this is my point. So our early strategy, when I was working in the Darmstadt, we were focusing on this high strain material. And the idea was really simple. Simply removing remnant strain will give us really high strain. So it could be the removing remnant strain could be done by introducing paraelectric at zero field, which is quite possible in the relaxed material, or you probably can utilize the phase transformation. And this repeating phase transformation will give you a really high strain. So this is our early achievement, how this large strain material is different from the typical ferroelectric materials. Okay, so it seems that time is really flying. So let me speed up a little bit. This is the current state of the art of achieve the largest strains in the lead-free piezoceramics at the moment. So as you can see, even though we have a large hysteresis existing here, this SMAX Emax value is really a lot above the normally achieved D33 values. But something I want to point out here is this our recent achievement here. SMAX Emax near 1,000 picometer per volt, which is already quite fitting into the real-time applications for high-end the practical applications. So I'm going to briefly talk about how we achieved this here. So the idea was simple. So we utilized the templated grain growth technique, but the difference between typical templated grain growth and ours is the type of templates here. Instead of using normal templates, we use the polarizable template, which means in this case it's a big particle. Big particle which has which is a ferroelectric with a polarization along A and B crystallographic direction. So That means the Curie temperature of this big particle is a lot higher than usual ferroelectric lead-free piezoelectrics. That's why during cooling, this material transforms into paraelectric to ferroelectric, so that they already have a spontaneous polarization along the A direction or B direction, in plane direction. So once the Curie point of this lead-free material is reached from the high temperature during cooling, this start to be this lead-free material automatically pulls along this direction. So that means that this spontaneous polarization can hold this entire spontaneous polarization in the lead-free piezoceramics, so that whenever you try to switch this spontaneous polarization of the lead-free materials, once you remove the electric field, it goes back. That gives you really, really high strain. So this is just an experimental procedure you can easily find in the reference I put in there. And here, this is MB particle we used. This material is a ferroelectric with a polarization, spontaneous polarization direction along A or B. And we use that, and as you can see, this SM picture shows a highly textured, the texture is really well fabricated. And we did the chemical analysis on that using SIMS, and we don't see really chemical inhomogeneous in this material. And this demonstrates that mechanism involved in this material. As you can see here, this is not typical ferroelectric domain switching, but the electrorestriction. The parameter changes during the application of electric field, and which is completely reversible. So it comes back. So this gives the really high strain, just like I show you here. So, and then finally, this is a summary of the properties we achieved. You see that our newly developed material has a lot better the temperature dependence in its functional property, Smax, Emax, and you see that this is a truly electrorestrictive properties, which means temperature stability is better, and this response time is really nice. And this was we already transferred this the knowledge to the industry, which develops the haptic devices out of this new material at the moment. So this is a summary, and sorry about this too lengthy webinar, and thank you for your attention.